Yes, you are. All right. Now, these are all antiderivatives. They're not definite integrals, they're indefinite integrals. Uh, I remind you, big picture, that when you integrate, you are undoing a derivative. So, for example, x squared is the derivative. What was the original function? Well, if we're undoing the derivative, then the power should go up. And so the original was probably 1 more, or x cubed. Now, would you agree that that doesn't quite check, because the derivative of x cubed would be 6 squared, and there's not a 3 there here, so it must have been 1/3 or x cubed over 3. Furthermore, I don't know if this had been plus 1. Could it have been plus 1 and had a derivative like x squared?
Yes.
Sure. Could it have been plus 2? Yeah, so we're actually getting a family of possibilities. We say all these things could be the same just by virtue of a different c, which would go away no matter what the derivative is, right? All right, so this is ye old power rule we just used. When you anti-differentiate, you raise the power by 1, divide by the new, which is the opposite of derivative, which is reduce the power by 1, multiply by that. Oh, how about that? Is this? All right, here we go. 1 over x, you know, it's natural log of absolute value of x. The reason is that we want to be as inclusive as possible. Just by saying it was natural log of x only, that wouldn't allow for negatives. But absolute value allows for negatives. And either way, the derivative would still be 1 over x. It would just have negative slopes here, attaching to there. All right, so absolute value. Okay, check. E to the x, you know, that's fine. A to the x. Some of these I want to get across to you again that you know a lot of calculus, but you know about 70% of calculus. Okay, so if I say what's the antiderivative of 2 to the x, you might not know that because it's set 72 and you didn't do set 72. So we have still some stuff to be covered later. Sine you remember, cosine you remember. Sine's the one with the negative, be careful there. Just check with derivatives. Do you remember tangent? Do you remember that? Okay, so I'm writing you a note there. It can be found by u sub, which we'll also talk about today. Tangent is sine over cosine. Wait. Okay, u sub is meant to unbreak the chain or undo a chain rule. It happens when you have two terms and one is the derivative of the other. So in this case, if you were to u sub this, you would let u equal cosine, and therefore du is negative sine of x dx. Now I don't have a negative sine of x dx, so I'm going to move that negative over and call it that. Now when I u sub then, sine of x dx becomes negative du, and cosine of x in the denominator becomes u. The whole idea of u sub is to get an easier integral, and so what's the antiderivative of negative 1 over u? Negative natural log of the absolute value of u plus c. We sub back negative natural log of what was u? Cosine of x plus c. Now that's an acceptable answer, but it's more commonly written as natural log of secant. How can that be? How is negative natural log of cosine the same as natural log of secant? Those are go.
Because secant's the inverse of cosine, and since it's a negative natural log, you can like move that up as an exponent.
When you say inverse, you mean reciprocal, yes?
Yeah.
Okay, that's okay. So, yes, exactly. That negative can be moved up to an exponent, log rules and all. Cosine to the negative first power is 1 over cosine, which is c. So you'll more often see it as c. Cool. Cotangent. You can find that same one by u sub. It doesn't have a negative. Secant of x is, wow, that's a humdinger. Boy, that's hard. That one's a deserted island one. And by deserted island, mean If I stuck you on a deserted island with that problem, it would take you about, well, you're pretty smart, maybe 8 hours or so before you said, okay, now I've got it. It's rough. It requires creativity, which higher math often does. It requires a very creative approach. We'll cover that later. We'll cover that later. Trig to an odd power. For example, you can integrate sine. Cool. But can you integrate sine cubed? That takes a little different approach. Sine squared. That takes a little different approach. Thank you. Haven't learned that yet. We'll learn that this year. These, I hope you remember this one is not crucial to me, but these two I want you to start to get in your brain. 1 over the square root of 1 minus x squared is arc sine of x, and 1 over 1 plus x squared is the arc tangent of x. Integrating natural log, that also we'll cover later, but that's actually, maybe you did it last year. Do you remember how to do integrate natural log? Takes a skill, I think you learned at the end of the year. It requires ultraviolet. Yeah, it requires integration by parts. So that we will actually touch on in a second, but my idea is that you have a lot of these known, but a lot of these still to come. Integration rules, just big picture. If you are integrating 2 separate functions, can you integrate each addend separately? Is that a thing? Can you do that? Can you split a sum? Is the integral of the sum equal to the sum of the integrals? Yes, that's true. It does work. What about a product? Can you split a product? Is the integral of a product equal to the separate integrals, the product of the separate integrals? Is that a thing? That's 100% false. No. Ooh. No. Okay? That's not a thing. If you have a fractional sum, if you have something like f plus g over h, this goes to more like algebra rules. Can you split that into f over h plus g over h? Wait, is that a yes? Yes, that's a yes. What if the sum is in the denominator? H over f plus g. Can I split the denominator sum up? H over f plus h over g. Is that a thing? No, that's just bad arithmetic, obviously. 5 over 2 plus 3 is not equal to 5 over 2 plus 5 over 3. Wouldn't you agree that's garbage? This is 1. That is not 1. Right? That's just bad math. Okay. Good there. What about constants out front? If you have a constant in the integral, then what can you do? Pull it up. That up. All right. Good deal. Tell me if you have questions. Let's do a pause for practice. This is verbal and analytical. A curve has a slope of negative x plus 2 at each point. Which of the following is an equation for the curve if it passes through the point 2, 1? Notice nowhere in this problem, which is an AP problem back in the day, does it say, hey, integrate. It doesn't just slap you across the face with it. It's kind of hidden in there. How would you approach this problem? To me, it goes to interpreting that first. Actually, let's do this on 2 different levels. Test strategy. Okay. Which of these, just looking at them, has a possibility as an answer? Which could have a slope of negative x plus 2? Which has a chance and why? Talk to me, people. C. C is the only one that it could be because it's the only one. What? Whose derivative is negative x plus 2. This guy, if it has a slope of negative x plus 2, doesn't that mean its derivative equals negative x plus 2? Well, that derivative would be x minus 2, that's a no. That guy's derivative would be 4x plus 1, that's a no. Negative x plus 2, that's a possibility. 2x minus 2, that's a possibility. And negative 2x plus 1, I'm sorry, that's not a possibility. I said that's a possibility, but that's not a possibility. And this guy, negative 2x. So you can actually do this just by taking derivatives of the choices, and that would be pretty quick, right? So method 1, derivative of each answer. Now, today's not derivatives, though, so I forbid you from using your brain to do it the easy test-taking strategy way. Instead, let's solve the problem analytically as if the answers weren't even there. All right? So, if the answers weren't there, what would you do? You'd integrate. Okay, so if the derivative, think of it like this. F prime is negative x plus 2. What's the inverse operation to differentiation? Integration, or anti-differentiation. So if I integrate both sides with respect to x, then f is the antiderivative of negative x plus 2. Why am I writing slanted? I don't know. So what's the antiderivative? Negative 1/2 x squared plus 2x plus c. Now I felt like they didn't do a very good job test making here because they should have given you a good distractor where you really had to integrate. But oh well. How do I find the c? Plug in the point. I have a family of different curves. I have a ton of different parabolas. I could nail it down by knowing, hey, not only does it have this derivative thing, but it also must go through T1. That nails it down. So if I plug in the point, I get 1 equals negative 1/2 over 4 plus 4 plus c. 1 equals negative 2 plus 4 plus c. So what does c equal, my friends? Negative 1. I agree. Negative 1. Okay, so it is c by virtue of what's the difference. With me? All right, cool. Now, fundamental theorem of calculus I want to talk about on lots of levels, but for now we're just going to talk about the most basic. What do you do? The most basic what do you do is you find the antiderivative, which typically is, in many books, is called capital F, but capital F equals the antiderivative, and then you evaluate it at the upper limit minus the lower limit. All right? So would you try that example and see what you get? Obviously, that's no calculator. You could do it quicker without the calculator if you know what you're doing. What'd you get? Pupils? Why are you so slow? You're supposed to be the brilliant kids. What's your problem? You're real rusty. Lily, you were done 10 minutes ago, right? No, you were done. Okay, what'd you get? D, 4/9 is correct. Make sure your antiderivative, when you go to check, make sure your antiderivative is correct. I did a rewrite step. You don't need to show that by any stretch, but I tend to work slowly. So x to the negative third rewritten, it allows me to use the power rule a little better, a little cleaner without mistake. I raise the power by 1, divide by the new, so that's your antiderivative. Then, whether you pull out the negative 1/2 or not like I did, that's up to you. You can leave it in, it doesn't matter, but you should get 4/9 for answer. Are we good? Yes. Okay, questions? Please, I don't want to go too fast and say you shouldn't be asking questions if you haven't had. Okay, let's go to the backside, ye old backside. Integration techniques. Now, besides just term-by-term integration, you also have a little bit of skills. There are by the time you leave my class, you'll have at least 4 different integration skills. USUB, which you already have, ultraviolet voodoo, which you already have, but probably need practice on. Then you also learn trig sub and hyperbolic trig sub, super valuable, and partial fraction decomposition, which that sounds just smart, just saying it, Mark. Oh, I just did some partial fraction decomposition today. No big deal. We'll do that later too, although you have done partial fractions in pre-algebra sense. I don't think you've done them in a calculus sense. So check this out. USUB. USUB is used when you have one of 2 possible solution cases. Now the case that really it's used for 90% of the time is when you have an anti-chain rule case where you have 2 functions, a product of 2 functions. Chain rule gives you a product, derivative of the outside times derivative of the inside kind of thing. So when you see that in an integral, it's maybe undoing a chain rule. The other that's commonly overlooked is what I think of, and it's not very mathy, but the unfortunate sum case. Now that, again, is just kind of my terminology, but imagine this. Say you had x times the absolute, or square root of x minus 2. Can you split a product into 2 separate intervals? Can I do that? No, you cannot do that. That breaks the law. Is one the derivative of the other? Not really. And yet, and can you distribute so it's all good? Can that be done? No, all those things that I would like to do are out. Now, that would lead me to 2 thoughts. All right, so I could maybe do ultraviolet voodoo, or maybe it's USUB with a little work. Here's the unfortunate sum. The sum is unfortunate because it's in the root. So if you were to USUB and let u equal x minus 2, then what would x have to be? If u is x minus 2, then x is u plus 2. And I also need my du. What's du? dx. Okay, now the reason that USUB works great here is that that x will be a u plus 2, but it'll be outside the root, and that's good. Inside the root is root u, and then I have a du. Now, by making that USUB, it changed where the sum was, and it allows me to now distribute, and this becomes u to the what? 3/2, and u to the 2u to the 1/2. Then you can integrate power rule and all that stuff and sub back. Do you have to sub back for u in an indefinite interval? Yes, you must sub back in an indefinite interval. In a definite interval, do you have to sub back?
As long as you change the bounds.
No, you change the bounds for u and you do not sub back. All right, so first, try this guy by USUB, please. Then do the definite integral by USUB. I'll be walking around. If you don't remember, ask me or your math amigos. First thing is to decide what is u. I don't know about you, but I'm getting D for the first one. How about you? Okay. If you don't get D, find your mistake or ask me. Otherwise, move on to the second 15. Let them say you so we'll be checking very common sometimes question. I don't know about you, but I'm not, after doing what if I just did the problem without seeing the answers, this is kind of what my answer would look like, but obviously the answer's not there. So what's going on? Yeah, so they're flipping these limits of integration. And when you do that, it is opposite. Why? Why? When you switch the limits of integration, why is it the opposite outcome? Yeah, going backwards. Now, when you go backwards, you're changing the independent variable in a negative way. So you do that because if you go backwards, du is negative. Okay, so that's why we negate that. So negative 1 to 1, 2 minus u, root u, positive du, is that there? Is that a thing?
It should be negative.
Oh, got you. I didn't take it yet. Negative d is still there. Now, if those two guys negate each other, whoosh, whoosh, then I'm feeling E. Is E feeling right? A is definitely not it. D could have been it with the right signs, but it doesn't have the right signs, so it is D. Success? ¿Cómo se dice success en español? Oh, success. All right, somebody asked, for Pete's sake, I should know that. All right, integration by parts, ultraviolet voodoo. Where's it come from? I know you're taught it, and I know it's at the end of the year, but where's it come from? Just somebody said, hey, I don't know, I'll just throw some U's and V's together. Is that how math works? They just say, there's no reason? No, never. That's English. In math, there's a reason. There's always a reason. So, say you had a product, and you took the derivative of that product with respect to whatever the variable was, probably of x, but who knows? You're taking the derivative of that product. By product rule, what's the derivative? First times the derivative of the second, so u dv plus v du, yeah? All right. Now, say you want to develop a rule. Okay, we know that's cool, the derivative rule. Say you wanted to figure out a derivative rule for products where it wasn't a use of or chain rule case, right? they thought, well, shoot, I also see products in the product rule. So if I were to say, let me call this UDV, and I rework the product rule a little, wouldn't this be equivalent to oops, this is, I don't like that, my bad. Okay, sorry, I did the wrong one. Say I keep this, move that, all right? So I isolate this. UDV would be the derivative of the product minus one of the terms of the product rule, right? You with me? Okay, now I'm trying to get an integration rule was their thought process. That's great, but now integration, well, if I integrate one side, it's cool as long as I integrate both sides. Now this side is going to be my theorem. The derivative of something is. What's the derivative over here? Well, or what's the antiderivative? What's the antiderivative of the derivative of UV? UV. What's the antiderivative of VDU? Well, it kind of depends. I don't know. It depends on the problem. But that's, in essence, where the ultraviolet UV comes from, is it's a reworking of the product. No big deal. Okay? In order to choose U, the question is often going to be, how do I choose U? One of these, when you go to use ultraviolet voodoo, the first thing that goes through your mind is say, all right, it's a product, but not a chain rule problem, because one's not the derivative of the other, so I wouldn't use this. Maybe it's ultraviolet voodoo. Then the question is, all right, which is U, which is DV? Well, in choosing U, it's pretty common to use either the acronym LIPIT or LIATE, depending on your teacher. Some people use LIATE. But LIPIT is an acronym for law. Now that's the best U, or natural log. Yeah, usually natural log. The best possible U is if there's a natural log in there, let U be that. Okay? The next best U is inverse trig. So if you saw arcsine in there, or arctangent, that's your U, as long as you didn't have a log. Okay? The next best is polynomial or algebraic terms. So x to some power. That's not a terrible U. Getting into the terrible U cases is exponential, like e to the x, and the worst U is trig, like sine or cosine. These are bad U's. All right, now then, using that as a guide, we have a product. One's not the derivative of the other, so we're going to ultraviolet voodoo that bad boy. Looking at the hierarchy, do we have a log term? No. Do we have an inverse trig term? No. Do we have a polynomial term?
Yes.
Yes. Okay, so x is the polynomial term, so I'm going to let u equal x. By default, then, the dv would have to be everything else, which is e to the x dx. Now, those have companions. If u is x, then du is dx. And if dv, we got that by taking a derivative. If dv is e to the x, then the antiderivative v is e to the x. Don't sweat the seed. All right, now, with those four things, I can say this is equivalent to, or exchange it for this, which should be easier to work with. uv, what is it? X e to the x minus v du, what is it? E to the x dx. Now, when you do ultraviolet voodoo, if this new integral is not better, then you did it wrong. The whole idea of ultraviolet voodoo is to get an integral that's better or easier to do. If that's not the case, then you have a mistake. Now, this is a definite integral, and so it has limits of integration. Now, I had at least two different, professors had at least two different ways of writing this. One guy, he put them in both places, 0 to 2 here and 0 to 2 there, and I'm fine with that if you approach it that way. Another guy that I had in Calc 2, he just put a grand set of evaluation bars outside, and that's fine. Either one's fine. as I am told, and I have seen actually both in books. So either way is good. Either way, we have to integrate. X, e to the x minus, what is the antiderivative of e to the x? E to the x from 0 to 2. If you evaluate it at 2, I'm looking at 2 e to the second minus e to the second minus the quantity 0 e to the 0 minus e to the 0. That right there is probably one of the greatest sources of lost points for Calc 1 students. They think constantly, they think, oh, well, 0, I didn't even need to look at that, because when you put 0 in, you get a nothing. Is that true? No, that's not always true. You do need to look at it, all right? In many cases, when you put a 0 in, it zeroes out, but in some cases, like this one, it does not. So we have a single e to the second plus 1, and so our answer is B. Run it in for the touchdown and spike it. All right, that's good. Is that good? Is that the end? Okay, that's the last. All right. How about test review? What do you say? What do you say? How you doing? Do we need to take a little walk outside to stretch your legs, or are you doing okay here? Okay. Here we go then. Let's stretch our legs. Let's go touch the corner of the tennis courts and back. Yes, I need it. Let's go.
chemistry this year because I like forgot everything over this question. Maybe got a 3 on the AP exam without studying. You didn't study a lick. I just said, well, we're gonna do this, and it turns out how it turns out, and I passed. If I actually studied, I would have done a lot better. But like, I was like, no, I'm just gonna take it as challenge, and it's gonna be a
All right.
I
Uh, So, oh, shoot. Content recording, there's a little test. So, my test will take a little bit of getting used to. It's an adaptation period. How did this candidate, she had 2 pages, right? Calculator, no calculator. My page is calculator first, was hers. Okay, that's pretty common. When you finish actually, let me say that, they should be roughly even, so you want to pace 25 and 25, unless I say otherwise. Although, I don't know, depends. Couple things about mine. Probably like Ms. Kenna does, the minute you go to get the no calculator page, the calculator's gone forever. You can then use it again for the test, all right? You may keep the first page and continue to work on it when you get the second page, but the calculator goes away for good. Cool? Is that how, like, she did it? Okay, that's how the AP does it. The AP exam is. Second, I am a terrible judge of test length, all right? So it usually takes students a bit to see that firsthand, but I'm going to give you a warning. So if you ever saw one of my test days last year for BC students, kids actually were usually, we're here within 2 minutes of their previous class, 3 minutes before the bell, because the time runs that long. And I can guarantee you, second semester, when the bell rang, every single student was already sitting and started the test by the time the bell. They hurry, the test is long, sorry, it is what it is, okay? Julia Trogovich, oh my gosh, she would just take the party for the next class. She'd work it like 10 minutes into the next class. We can't do that. That's just a no. I got major head from other teachers. So just be aware that length could be an issue. Pace yourself well. The test pages are weighted equally, so there's no reason to sabotage yourself for the second page in favor of the first page. Just be smart about your time. Let's see. In terms of the review, this has what I expect you to know within reason, and although it's not exhaustive, it's examples and some practice problems. Students tend to just blow off the first page and say, what are the practice problems with folks there? I wouldn't do that. If I were you to prepare for college, you should look at the list and think, all right, what does that mean? Because that's more common instead for the professor to say, hey, this is when the test is over, it's done. Practice problems were rarely given in my courses, at least for higher level courses. Freshman, sophomore, maybe, but junior, senior, yeah. The practice problems are good practice, but not exhaustive practice. So, don't you dare come to me and say it's with a problem on the test and say, hey man, you put that on the test and it wasn't on the review. This is not a practice test. It's practice for the test, not practice test. And so don't think it's an algebra 1, which most teachers that practice. There's no practice test, okay? It's practice for the test. I will post my key to my website tonight so you can see how it's done. And I will be available tomorrow morning before school. Also, maybe a little different than Ms. Cannon. I don't know, when she reviewed before school, did she have a prepared review or did she just take questions? Oh, super, that's what okay, so that is good. Don't come in and think, okay, I'm here for the review, tell me what's on the test. Again, that's enough, okay? If you have questions on the review, or I don't give you practice on whatever intermediate value theorem, or you weren't sure what I meant, then feel free to come in and say, hey, I'm okay on the review, but I wanted to go over this, or I had a question on that. it's you guided and we go from there. Understood? That's about it. I was trying to look up last year's averages, but I think the first test goes pretty well. Don't sweat, just do your thing. Okay? You're here because you're brilliant, so just keep being brilliant. Make good practice. That's it. Get yourself some sleep. So a few things. I wanna expound on a few, or expand on a few of these things. Not expound, expand on a few of these things. Trig facts. You should know all 6 trig facts at all referencing, right? So if I ask you cotangent of 2 pi over 3, you should know that is negative root 3 over 2. Okay. Anyway, trig graphing. This has been an issue. I am picky about that, and that'll be on there. And some of you still are not there, so I would go over that. If you don't see a practice problem, you want one, I can help you with that. Parent graphs, most of you know the parent graphs fine. Transformations of graphs, shifts, reflections, and all that. That also is fine. And intermediate value theorem. You guys do that pretty doggone well, I gotta say. Once again, good job, Miss Karen. For limits, one-sided limits, graphically, analytically, I guess maybe vertically, but not vertically, verbally. The limit does not exist. There are 2 reasons the limit doesn't exist. What are they? That's differentiability. You're thinking differentiability. One-sided limits not equal or oscillation. Okay, both of those are typical reasons that the limit doesn't exist. If I ask you, if it's not a multiple choice question and it says in the direction, if you say the limit doesn't exist, justify that, then you need to justify that, and I do mean with good limit work. So for example, if f is x plus 2 for x is less than 0 and 3 to the x for x is greater than or equal to 0, and I say what is the limit as x goes to 0, and I set in the directions, if you say d and dy, and you would have to say something like the limit as x goes to 0 from the left. Anytime you use a piecewise, good work says identify the piece that was used, so don't call it f of x. Say, for this region I'm using x plus 2. Call it, what limit? What is that approach? 2. The limit as x approaches 0 from the right is 1, and so you would justify by saying something like d and e, the limit d and e because 2 is not equal to. All right. 2 famous limits. The first one is sign related. Do you remember it? The limit as x goes to 0 of sine of x over x is 1. Okay? I don't know if you even know that, but in physics you use that idea all the time. If I asked you what's the sine, approximate the sine of 0.003, you would say it's about 0.003, because for very small angles, these are roughly the same. Okay, can you use that once in a while for small angles in physics? You'll see that later in the semester. We'll talk about that. The other one is less known. It's cosine e, and so it's the limit as x goes to 0 of, sometimes it's cosine of x minus 1, sometimes it's 1 minus cosine of x. It doesn't matter. It is still what? All right, then. You would probably use a table if you didn't remember, but it is 0. Okay? You should be able to evaluate a limit graphically, analytically, numerically. If it says numerically, I mean show a table, make a table that shows the limit. Your first is analytically. So if I gave you this, direct substitution is my first try, but direct substitution yields 0 over 0. So then you say, all right, what should I do? Well, I'd say either do some algebra or pick up the table. Well, preferably you would do some algebra. So what would you do? Factor out x minus 2, you'd be left with x plus 2, so the limit is, oh, okay. I would prefer that than you using a table. Use a table as a last case. Sandwich theorem. I gave you practice on the sandwich theorem. I think it's towards the bottom of the page, so make sure you can do that. Connection of vertical and horizontal asymptotes. If the limit as x approaches a constant of a function is either dne or infinite, actually, let's say this. If it turns out to be this, which is infinite, could be positive or negative infinite, then what does that imply graphically? There is a, draw a picture. Here's a constant x, y is going towards infinity. It is a vertical asymptote. You need to recognize that. You also need to recognize a horizontal asymptote in its connection to limits. A horizontal asymptote is end behavior. As x goes to infinity or negative infinity, f of x approaches what if it's a horizontal asymptote? A constant. Okay, a constant. As we go this way, it starts to approach a constant. Okay. Definition of continuity. You must be able to show something is continuous with limits. If I don't see limits in your continuity proof or justification, then you will get practically nothing, right? I don't want to just see numbers thrown out. What are the three types of discontinuity? Jump violates the left-hand, right-hand limit rule. X approaches C from the left. X approaches C from the right equals f at C. Jump approaches the left-hand, right-hand limit rule, or it violates the left-hand, right-hand limit rule, so that's why it's a discontinuity. What's another? Vertical, not tangent, that's differentiability. Asymptote, okay, so that's an infinite discontinuity. It does represent an asymptote, but that's usually called an infinite discontinuity, where f at C doesn't exist, and the left-hand, right-hand limits are infinite and therefore don't exist. What's the last? Jump, infinite, and removable, which is code for whole. Okay. Which of the parts of the definition is violated by removable? Yeah, f of C is violated. It's not equal to f at C because there's a hole. The left-hand, right-hand are cool, but the f at C point. All right. Derivatives. You should know the three definitions of the derivative. The first definition, the alternate definition, and the symmetric definition. And recognize them in limit form. So if you see something like the limit as h goes to 0 of 3x plus h squared minus 3x squared over h, you would tell me that is? Yeah, it's the derivative of 3x squared, which is 6x. Okay? All right. You should be able to estimate a derivative from a table. If I told you that f has values like at 0, 2, and 3, and 7, 9, 11, and I wanted you to estimate f prime at 1, okay? I don't know if I've said this before, so I need to make this clear now. These are things I look for. First of all, if you say this is equal, you're out. Okay, it's an estimate. And that's on the AP test too. They are very picky about when you are asked for an approximation, you show that it's an approximation. All right? So I'm telling you, I'm warning you right now. Don't give me some wussy, oh, I'm not really sure if it's an approximation, so you choose. Or it's kind of wavy, but all of those minus. Okay, I'm talking intentional. This is an approximation, baby. I want to know and definitely see that it's an approximation all of these are judgment calls, and if I have a judgment call, I judge against you. Understood? Cool. All right, so this is an approximation. Second thing, just good math and AP, do not go straight to the table. Show me where your values are coming from. So I do not want to see 9 minus 7 over 2. I don't want to go back and figure out where those came. Nope. I want you to show me what did you do. So f at 2 minus f at 0 over 2 minus 0. That I need to see. The calculation, I don't care. Show it if you want, don't show it. I don't care. Do it mentally, whatever. But this, that I gotta see. And so what is it? It's 1, yeah, okay? So the rate of change is approximately 1. We're using an average rate of change as close as I can get to 1 to approximate instantaneous rate of change. Oui, oui? What do we got here? We got 45 minutes. Boom. Okay. Prove this. I anticipate probably not going well for some. Prove not differentiable. Prove it. Not say it, prove it. What are our 3 reasons why a function would not be differentiable? Sharp turn. Vertical tangent, not asymptote, vertical tangent. There's rise but no run. And what else? Say again? Discontinuity, yep, exactly. While we're on the vertical tangent case, say you had dy dx and you had some kind of, whatever, maybe use an implicit derivative, 3y minus 2x over x plus 5y. Okay? There would be a vertical tangent where what happens? Where would you get a vertical tangent? It goes vertical if your derivative or your slope is undefined. Yeah, so rise but no run, which would mean you get a vertical tangent where what happens? X plus 5y equals 0. Okay? You would have an, what does a numerator 0 mean for you? Flat. Okay, so you'd have a horizontal tangent where there's rise but no run, and that's when the rise equals 0. So that would be when the numerator equals 0. Now that's a pretty common AP question. Find where the tangent slope is vertical or horizontal. Besides satisfying this condition, it also has to satisfy the condition that points you're talking about are actually on the original curve. Okay, so if I said, hey, where is 2x squared plus 5y equals 7y squared minus 4, have a vertical tangent, you would first have to find where dy dx is undefined or where the denominator of dy dx equals 0, yeah? But after that, then you'd also have to say, okay, well, that's lots of different xy relationships. It also has to satisfy that it's on the curve itself. If you're not quite sure what I'm talking about, you'll see soon enough. All right, taking the proof not using the definition of the derivative, proving a derivative doesn't exist. That is, I did give you a practice problem on the back of that, so you might practice that. You might need some practice on that. Taking derivative, you guys will kill the technique. I mean, you can use the power rule, constant. Your technique is excellent. I'm sure you'll be fine there. Those will be layups. Taking an implicit derivative and finding where its tangents, horizontal or vertical. We just talked about that. I talked about that ahead of time. Related rates questions. I don't know whether you know it or not, but related rates are usually one of the hardest questions for top 1 students. And yet for you guys, they're usually one of the easiest because Miss Cannon teaches that better than anybody I've ever met. She is amazing. So you guys will be great there. Mostly just remember that you're differentiating with respect to time there. And then last but not least, critical numbers and extrema by the first or second derivative test. That's where showing where the first derivative changes negative to positive for a min and positive to negative for a max. The test does not include second derivative, which we just talked about a couple days ago. All right. If you have any questions about what about this, is this on the test or that on the test, let me know. Let the back has practice problems that might help. A lot of those are from CU exams that I had. So they're good problems. And that's good. Questions on the test? Okay, just show up and be brilliant. Just be yourself. You're here for a reason. Boom. How about last part of the lesson? Review homework 8. How was that? Super fun or 2-hour struggle bus? All right. Okay, 6-hour struggle bus? Wow. Your struggle bus just broke down completely, pretty much. Flat tire struggle bus. I did have the answers you didn't have online, but I'm happy to. So first of all, are you able to access my website? Can you see it?
Yes.
Okay, because I still have a couple of AD students that have trouble. I don't know if it's I'm not doing their part right or it's I don't know what it is, but as long as you can see it. So let's hit questions. This is hard, so just here we go. Yes. 10. Okay, so that's box 10. Yes.
Yeah.
Okay, box 10. Yep, good deal. This one I should have probably given you a hint on. Let me get a textbook. Okie dokie. All right, so while I'm getting situated, some of you, I imagine, besides being engineers, just because you're great at math doesn't mean you have to be a science engineer person. There are tons of applied math jobs, and boy, those people that run numbers on Wall Street, hedge fund managers, they're awesome math students. Those are math people, okay? So you can actually be one of the richest people in America just by being a math person and going to business school. Now, that said, many business schools, but not all, want you to take business calculus, although most of them excuse you out of it if you pass, especially the BC exam. That said, just in the interest of preparing you for your career, if I were you and you wanted to be a math person, a business person, I would probably go to my school's website, find their Calc 1, Business Calc 1 class syllabus, and look at everything they have. If they have problems or class notes or tests, I would look at those and say, yeah, I think I could do that. It's just got a little business slant. Some of it's just getting over the vocabulary. I got to say the calculus would be nothing for you. Business calculus, the calculus itself is nothing. It's just the vocabulary of the business that you might want to brush up on. But I still think if you were my daughter, I would say don't take business calc, just test out of it and take the credit. But do look over. So in number 10, so you are part of some kind of delivery company where there are two costs, which they are simplifying the problem greatly, but there are two costs for this company. There's fuel costs and wages costs. Now, actually, I should go back here. Let me read this carefully. Find the speed V in miles per hour that will minimize costs on a 110-mile delivery trip. The cost per hour for fuel for the van is C dollars, and the driver is paid W dollars per hour. Now, just so we're clear, when you drive, obviously you use different fuel at different times, and if you drive inefficiently, which I guess they most teenagers do, you accelerating up to a stop sign, slamming on the brakes, accelerate up the line, you're getting, I could out gas mileage you by a ton, people. You could get 23 or 30 out of your car if you would just coast forever, coast, okay? Not to mention the brake savings. My point is this: fuel varies with speed. If you are gunning it, your car is not working as efficiently. So cost depends on your fuel consumption, and that depends on your velocity. In this case, is it 21 or 22? In 21, they say the fuel cost function, actually, I should say this, fuel cost function is C equals V squared over 600, and that is cost as a function of velocity. And so that's in dollars. Okay. They also say that the wages of the guy are $5 per hour. All right. Now, actually, we want to find a total cost. I shouldn't call this, I have two different C's going on. So let's just call this total cost. Total cost depends on fuel and wages. I looked at this and I got a little confused and I started thinking, what the heck is going on? If that's the case, I suggest you start very general and work towards the specific. Trying to go too specific too fast is bad. So for fuel, it is V squared per 600, and that is already in dollars. So that is dollars already, boom, I'm done. Okay? Now, the wages might have been your issue. What do the wages cost? $5 per hour, but then the units are on, it's $5 per hour times. Okay, so it's not $5, it's $5 per hour. Use the units as a guide, and then you'd have to multiply that by time in hours so that you would actually get a money and money calculation going on. So the cost function or total cost function is V squared over 600 plus 5 times the time. Right? So by going fast, you might help yourself with the wages, but it will hurt you with the fuel cost and so on. Now, we're trying to minimize cost. All right, so you're through our first hurdle. Now what do I do? Should I start taking the derivative or do something else? Yeah, I want to get it down to two variables, so let's replace t. Why replace t and not v? Because the question asks for v. All right, so we want v to stay, we want to replace t. So what is an other v-t relationship that we can use to sub in? Read the problem carefully. It said something about a distance, right? It was 110 miles. So if, I don't know if you use distance is rate times time, or if you're a physics person, you said x equals rate times time, but whatever, wouldn't you agree that 110 equals the velocity times time? So if we sub, then time is 110 divided by whatever the velocity is. Now if that goes in, can I get a one variable equation? Only v squared over 600 plus 550 v to the negative 1. If I take that 5, multiply it by 110, and I just write v in the numerator. It doesn't, if you have lower v, it's fine too. Power 1, no? You with me? Yeah. Okay, now what do I do? Is that good? Are you good from here? Should we keep going? Continue? Okay, so different v's feels like, I don't know exactly what the shape of these looks like, but it seems like different v's will result in different costs. I mean, if you have this v and this v and this v and this v. So my goal is to find, all right, what's the minimum? And so I really need to know when cost stops decreasing and starts increasing. That's the best case, the least cost. So I want to minimize by finding where does TC prime go negative to positive, right? So take the derivative. What is TC prime, or whatever you want to call it? If you use different notation, that's fine. What's total cost prime? V over 300. What else? divided by v squared. Okay, do we all agree with that derivative? Okay. I want to find critical numbers, so let's proceed on there. I have something like 300 v squared, and this would be v cubed minus 550 times 300. And I want to know where this is 0 or undefined. It would be undefined if v is 0, but that doesn't mean whatever you mean by not moving. So that's a non-issue. Let's focus on the numerator. The undefined is a non-issue. Let's look at where v cubed minus, what do we got there? 165 with 3 zeros. So v cubed is 165,000. So v is the cube root of 165,000, which is 10 cube root of 165. So maybe, I remember getting 10 root 11 or something. Am I remembering this wrong? What did you get for an answer there? How do I remember?
I think that was another problem.
Oh, yeah, that was on the front side of those. Okay, sorry, I was thinking. Does that come out right? Okay, cool. What is the cube root of 165? Between what, 5 and 6? Yeah. Okay. So 50-ish. All right. I'm still kind of getting back to my groove explaining stuff. Did that make sense to you? Okay. Other questions? What? Yes?
The part B of 1.
Part B of 1. Okay. Yeah. Oh, I thought part C was, oh yeah, there's no C. Dumb. Okay, so cool. Good question. This is pretty common free response or multiple choice question, and these always have very low averages. And with practice, they're pretty okie dokie, all right? First of all, I needed to introduce a word that's commonly used in calculus texts in college at least, and that's monotonic. If a function is monotonic, then that means it has one sign. And so if the first derivative is monotonic, it has one sign, which means the function will either always be increasing or always be decreasing. And if the second derivative is monotonic, again, either the second derivative is always positive or always negative, so the function's either always concave up or always concave down. In this case, they're telling you the first and second derivative are monotonic. You're going to have to think of this on two levels. Here's g of 4, we don't know. The table, does it indicate that the first derivative is always positive or always negative? Always positive, okay? G is always increasing, and so that implies that g prime is always positive. Now that tells me that in going from here to there, g at 4, if it's going to always be increasing, g at 4 must be greater than 19, where it was at 3. G at 4 must be greater than G at 3, so it must be greater than 19. Now, that obviously could be a million different numbers. Could it go infinitely large, or is there an upper bound for it? That's the harder one. So let's go here. Look at the changes in the table. This change is change is 5, yeah? Then the change is 4. Now, what does that tell us? Now, if I look at the change, then you could say that the change in G is like G prime. G prime roughly, or could be approximated as 5 in the first region and 4 in the second region. It's probably varying, but I know the change is going from 5 to 4. Well, isn't the second derivative then the change in G prime? So how are these going about? Are these changes increasing or decreasing? Yeah, the changes are decreasing. And they must always be decreasing because the second derivative must always be negative. Now, that means that the next change must be less than, does it have to be 3? Don't read into it too much. Does it have to be 3? No, it has to be less than 4. So if it has to be less than 4, you're a step ahead of me, but yeah, I see what you're saying, 23. The next change has to be less than 4. Well, if we're at 19 and the next change has to be less than 4, then we have to end at less than 23. Okay, so G at 4 must be less than 23. That can be put together. G at 4 must be between 19 and 23. Okay, that would usually be a multiplication. That make sense? Other question? Yes. Box 5. I'm surprised nobody's asking about the box problem itself, speaking of boxes. But box 5, Larson Hofstadter number 19, yes? Is that, am I looking at the right problem before I was? No, that's okay, but is that the right problem? 3.419?
Yeah.
Just making
Oh,
sure.
49. It's 0.449.
You said box 5.
Yeah, it says 49.
Oh, wow. Sorry, I made changes. Last year's key was totally different. Okay. Shoot, good thing I got that clear then. Okay, here we go. 3.449. I don't have that up here, so I'm going to turn the slide. 3.449. All right, that's the problem, right?
Yeah.
All right, let me find that. I don't remember that, which now I'm getting a little scared. I hope I can do it, but I can. Thank you, Ms. Walker, for teaching me calculus. I have faith in myself. 49, here we go. Okay, I'm giving you a cube graph. That cube graph, yeah, I should have probably done an example of curve sketching, doggone it. It is very much a thought process. So this cube has a max just about there, not quite. And somewhere in here. Okay, this is f of x. All right. Your goal is to sketch f prime and f double. Now, the first layer, the first one is to, if you know the shape, use that to your advantage. What does it look like f is? It looks like it's a cube, right? So if I use that to my advantage, then I would expect the derivative to probably look like some kind of parabola with stuff going on. Obviously, it's not that simple, but stuff going on. And f double is a line, okay? So I would expect to have kind of parabola derivative and linear second derivative. Cool? Now the question is where and what do they look like? That's where the calculus knowledge comes in. This is the big idea that I want to go in your head here. Where f is increasing, f prime is positive. Where f is flat, f prime is 0. And where f is decreasing, f prime is negative. Let's start here. The graph goes flat here and here. That would mean that the derivative at those x's is 0. So I'm going to nail some zeros or points down. If you put that on the axis, fine. It's ballpark estimate. In here, the derivative has to be 0 there. All right? Now let's use the other ideas. Where the function is increasing, remember you always read left to right. When the function is increasing as we go left to right, the derivative is positive. Well, in this region, the function is increasing, so the derivative is positive. I would show that graphically by saying the graph is above the x-axis. All right, I'm going to solidify this in a second, but I just want to get the basics. So what do you know between the max and the min? The derivative is negative. It's decreasing there, so the derivative is negative, so the derivative graph is under. How low? Don't sweat. Okay? And after that min, the graph goes back to increasing, so the derivative is positive and above. All right, so that combined with a parabola shape, I would say something like that would look good. Does that make sense? All right, now for the second derivative, you actually have two ways to go about it. You could apply that same thinking of derivative behavior from the red graph to get the green graph, so just do the same. I guess you could also use the concavity of the original function and do it that way. It's up to you. Do you have a preference of concavity of the blue or derivative of the red? What? Concavity, okay. So up to this, it feels like there's a inflection point-ish here. And so what is the second derivative? Where there's f has an inflection point, you know the second derivative it's probably changing, it's changing signs for sure. For polynomial, it's probably equal to 0, okay? So I know that at that inflection point, the second derivative is going to be at the axis. Where f is concave up, the second derivative is above the x-axis. Oops, yes. That was above the x-axis. So, is it concave up to the left of that inflection point or the right? The right, and so it's concave up or positive here, and it's concave down on the left side, so the second derivative is negative there. Linear left. That's thought. Does that make sense? Okay. Other questions? Yes, ma'am. 9? Is that box 9? Okay. Box 9. Oh, yoy. So, first of all, I had 3 people ask about this, and every one of them did the problem before it in the book, not after. I think maybe it's what you're thinking, but the question says, box 9, 3.730, is that the right problem? Okay. It says find or maximize the area of the rectangle that can be inscribed in a semicircle with radius r, not 5, okay? The one before it was 5. This said radius r. So if you have 5s and 25s in your work, you did the wrong problem. Okay, that was number 29. All right? So, I'm big on math history. If they had a math history degree, I would get it. But check this out. If you have circles and rectangles, what do they call that study? They call that geometry. Okay? If, however, you have x's and y's, what do they call that? Algebra. Now, if you got those two together, you would make what's called analytical geometry. And it is beautiful. You have all these shapes and shape knowledge, but by putting it and combining it with algebra, it opens a ton of doors. Now, for this problem then, yes, give me a semicircle and give me a rectangle, but lay it over the coordinate plane so we can use all those algebra skills. So don't, first of all, when you go to doodle a picture, don't just give me some floating geometric figures, draw them on the coordinate plane. All right? Now, if we look at the question, we want to, when you do optimization, I usually start with the picture and the question. They want me to optimize what? Isn't this a thing? Isn't it supposed to erase? Oh, yeah, okay, the area of the rectangle. Area of the rectangle. Is it xy or 2xy? What is my 2xy, really. 2xy. I want to maximize. The circle, so here's some x and here's r. Now, depending on how I make x, I could get different rectangles, and I would probably get different results as a result. If I make x really small, then I get no area. If I get x really large, then I get no area. So between an x of 0 and an x of r, I'm getting different areas, and I'm feeling like there's a best case that makes a match. Do you agree that the domain for x is between 0 and r? Okay. All right, then. Let's proceed. Do I want to optimize the way it is, or do something else first? Something else first, and that is Substitute another relationship. What's another relationship? All right, beautiful. X squared plus y squared equals r squared. Solve for y is the square root of r squared minus x squared. I'm taking the positive root because I'm looking at a semicircle in the top half. If I throw that in IE, then I get area is 2x root r squared minus x squared. Just so we're clear, x is a variable. It can vary. R is not a variable. It is a constant. It's an unknown constant, but it's a constant. R doesn't vary, right? Okay. Now, I'm going to differentiate a prime. Is that a prime dA dx or dA dt? dA dx. X changes with different, area changes with different x's, all right? So it's not related rates. Product rule, I assume your derivative went fine. First stays the same, derivative of the second. Actually, this is no picnic. Possibly you made an error. Probably not you, Sydney, but possible for me to make an error. Looks something like that. That's my derivative. Really, the cleanup is the key. If I clean this up carefully, I get something like negative 2x squared over the square root of r squared minus x squared plus 2 root r squared minus x squared. Stop me if you disagree. Okay. I want to know where this is 0 or undefined. I don't see it yet, so I'm going to do some algebra. If I get a common denominator, then I get negative 2x squared plus, when I get a common denominator, it is that. When I multiply by that, I get 2 times a normal r squared minus x squared, a root times a root is to the first. Wait. Okay, if I simplify, I get negative 4x squared plus 2r squared over r squared minus x squared. My critical numbers. I get undefined if x equals, I get undefined if the denominator is 0, and that would be happening if x is r. Now, what kind of area would that be, a max or min? Yeah, if x were r, if x were r, then the rectangle would be laying right on the axis, and the area is 0. That's a min. 0, a prime equals 0 at the numerator zeros. Well, if negative 4x squared plus 2r squared is 0, then x is 2r squared over 4 square rooted. What is that cleaned up? I'm thinking root 2 r over 2, or if you like, r over root 2, whatever. I don't care. I don't care if you're rational. Do you agree with my x? I could show that that's a maximum. And if my life depended on getting this right, I probably would to verify it's a maximum, but I'm telling you it is a maximum. Right, so now just answer the question. The question doesn't say, hey, find x. It says, what are the dimensions? The dimensions are a base and a height. The base is 2 x's, not x, but 2 x's. And so what is the base? Root 2r. Okay, the height is y, and y we said is square root of r squared minus x squared. That's r squared minus that big stinking yuck, r squared over 4. That simplifies to 1/2. R squared minus a half r squared is 1/2 r squared. So something like r over root 2. The height is r over root 2, or r root 2. Other question? Come on, you don't have a question on the box problem, I have. Come on. I look at your boxes and I think you should have a question on the box problem. Okay? So whatever this is, number 11. I'm not going to make you ask, but do we need help on that or not? All right. My first issue is I see a lot of new boxes, and I assume what was going on in your head is you really want me to make a box? No, probably not. Well, you answered wrong. Do I really want you to make a box? Yeah, I really do want you to make a box, just like that, or whatever you do, okay? I'm a little picky about this. I worked as a mechanic for 7 years before I became a teacher, and I can tell you that whoever designs a Hyundai back in the day never worked on a car, because you would never design it that way if you were working on it. It's knuckle banging muck, I tell you what. I hate engineers that are in their little office and designing little great things, and meanwhile, when they actually get put into play, the person that uses them thinks this is terrible. This is terrible. So if you become an engineer, would you please take a little time to actually work with the thing you're making and get away from your paper and pencil? Because, geez Louise, it's a good engineer is good with paper and pencil and in real life. So, I did want you to get some practice actually making a thing. Easy thing. If you were to look at a box with a lid, much harder with the lid, right? Yeah, it is. Okay, now, I'm going to call this width, length, and height to begin with. Let's first deconstruct it, or make it into a two-dimensional figure, sometimes called a net in pre-algebra. If you were to take the lid up, then it would look like this, yes? And then if you were to then further unfold it, then this lid might come all the way down, have that left side, then the base, and then if you were to take this right side down, it would be here, and if you were to unfold these flaps, they would be here. Okay? So a net of a box with a lid looks like that. Cool? Now, if this comes from a piece of paper, then this blue represents the paper from which we cut the box parts. And I did expect you to cut origami masters. I had people check, oh, see how they fold this. This is not an exercise in origami. All right, although it's great, that's not the intention. So let's go there. Gosh, let's call this, for sake of ease, I want to ask you to make the height x. Now, when you go to look at this, isn't this, every one of these little guys, an x, yeah? All right, so over here, every one of these little guys is an x. X, 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 x. We? Okay, let's talk about the width and the length in terms of x. You had to measure this, it's up to you, but I thought 28 centimeters. Okay? This guy, again, it's up to you. You could definitely disagree with me here, but I felt 21.6 centimeters here. If your answers, or if your measurements were different, then you obviously will have different outcome than what I did. All right, now then, I want to maximize, come back to that in a second. I want to maximize volume, which is length times width times height for a rectangular prism. Now that's four variables. Let's get it down to two. Let's make everything in terms of x. The height is already x. Cool? The length, here. I'll do it in green. Here's the length. 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 What does that green segment look like in terms of x? It's this way, so it probably relates to that guy. What is it? 21.6, take away 2 x's. The length is 21.6 minus 2 x's. What about the width? Width, 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 width. What's a relationship of the width? Or an equation based in x of the width. The width is, or give me any equation we can solve it for x. Okay, all right, so wouldn't you agree that 28 is equal to 2 widths and 2 x's, yeah? So 14 equals a single width and a single x, and so x, or w is 14 by 6. All right, now you have a volume equation of X only. You should be rolling however you choose to do it. I don't care if you multiply it out or if you use the product rule. It's pretty gross numbers. I might use the product rule. I don't know. It's up to you. But do you agree that to get a max, you want to know where V prime goes? Positive to negative. Now, in terms of what do I expect you to be able to do with or without a calculator, I want you to find V prime. But you may solve, what kind of equation will you get for V prime? This is cubic, so you'll get a derivative, that's square root of quadratic. You may use your calculator. Calculator for the quadratic solution to the derivative is okay. You may not throw this into the calculator and find the minimum, maximum, curve unless you calculate. Okay? Understood? Okay. That should get you rolling. Then you need to measure the box and cut the box and take the box and chop, chop, chop. I'll come around and look at that in just a second. Actually, might as well do it now. I'm going to just come around and see if you have the box made. I'm going to check you off now so you don't have to tote your box all over. I used to decorate my whole. It's not based on it being beautiful, it's being done. Is it done? It's not tape. Oh, you didn't want to get rid of it. Oh, well, that's one thing. Should I come back? Oh, you ripped it. What's the rip? Is it a lot of work to get this? Oh, I have scissors.
Well, no, I've already started ripping it. I might have to continue to rip it.
No, I don't think so. I think go for
That's
perfection.
nice. Oh,
Try it for perfection.
wait, no?
Use scissors to cut. That's almost got you. No, it's because of you do not have to read it, but I would try and see. Anybody's Okay, who else you got? You got that?
Okay, okay.
You are, not, you're respect. Respect what happened, that was like something. Oh, find where you went off.
4.031 centimeters. They can bring it down right here.
Oh, I didn't
Yeah, I made the box before I did the album.
That's part of engineering also, so you know where you want to go. Back to the drawing board. You do not have to redo it. Okay, Chase, check. Now, Sam, Steve, do you have it? Got you. All right, Ethan. All right, now, would you be interested in knowing that what you have there and what I did there is not actually the best, most efficient possible volume? I taught this class 4 years, and every box looked like this. But then I had a student, Emily, I don't know if you know Emily, but she came in here, totally different approach, and she could actually prove that her volume was better than mine. And what did she do? Now, this is before I said flat, but when you do an open top box, isn't it more like this kind of approach? Yeah? You with me? Are you with me?
Yeah.
Okay, which is the much easier case. Well, she, and I feel like it was cheating, but she divided the paper in two without cutting it, and she did two open top boxes and closed it, so it was more like two boxes on top of each other. That doesn't look right. Like this. And that actually has superior volume to the front. And that was awesome. And that's why she's at the University of Chicago right now, which is the best math school in the country. But yeah, so just so you know, thinking outside the box. All right. Anyway, I went Mr. Murphy on you there for a second. Okay, other questions? All right, I'll walk around. If you have any questions, let me know. How do you tell she's supposed to use it? How many do you use it for?
Frustrating.
Perfect. Okay, if, now, sorry, you can still do that box and show me later, or show me tomorrow, whatever, but, yeah, I still do expect you to do the box. Maybe 5 homework points if you want to throw it away. Okay. But, if you decorate it and you get a special extra attaboy, I know that if you want attaboy and attaboy, if you color it. No test points,
Yeah, we do.
have a great day.
My nerves so bad. It's like stats and this. Also, I can't. I'll get you this by like, start it out, okay?